To successfully execute an endovascular intervention, an operator must solve a strict mechanical problem. A delivery tool must be soft enough to safely navigate a tortuous vascular labyrinth, yet rigid enough to physically support large-bore devices like stents. This tension dictates the clinical taxonomy of guidewires. To meet these conflicting demands, guidewires are manufactured into two absolute, non-interchangeable categories. The first category is the non-steerable wire. These are engineered exclusively to act as rigid, supportive rails for tracking catheters into place. Because of their rigidity, non-steerable wires are strictly contraindicated for negotiating tight stenoses or selecting branch vessels. Pushing them into unmapped territory guarantees tissue damage. The second category is the steerable wire. These feature distinct geometrically shaped tips. By applying torque to the base of the wire, an operator can turn or flip these tips to selectively enter confined anatomical spaces. Memorizing trade names will not help you choose the correct tool. Proper guidewire selection requires analyzing exact dimensional geometry and material stiffness, and mathematically matching those properties to the patient's specific vascular pathology. We start by establishing the foundational nomenclature of guidewire dimensions. Industry manufacturing follows a strict measurement standard. A wire's diameter is always measured in inches, while its total length is measured in centimeters. The standard baseline length for routine clinical applications is 180 centimeters. When an anatomical route is complex or highly extended, operators switch to the 260 centimeter wire. The 260 centimeter length has specific primary indications. It is required when accessing the upper extremity originating from a groin puncture, and when exchanging catheters deep within the visceral circulation. It is also the necessary secondary choice for operations utilizing guide catheters longer than 90 centimeters, or when executing a through-and-through technique, commonly referred to as body flossing. This typographic equation shows the absolute mathematical formula required to calculate safe minimum guidewire length prior to a procedure. The minimum length equals the length of the catheter plus the length of the guidewire already inside the patient. This anatomical diagram illustrates tip geometry, specifically analyzing the mechanics of the J-shape design as it approaches a bifurcation. The sweeping physics of the J-shape ensures the blunt, curved edge makes initial contact. This prevents the sharp leading point of the wire from digging into or dislodging jagged vascular plaque during forward advancement. J-tips are classified by a specific geometric metric, usually labeled as 3 millimeters or 15 millimeters. This numerical value explicitly denotes the radius of the curve, not the total length of the tip itself. This dictates a strict geometric rule of thumb. Small curve radii will inadvertently fall into and select small branch vessels. Large curve radii will safely bridge across and bypass those same small branches. A classic scenario testing this geometry involves the profunda femoris, the deep artery of the thigh. To safely bypass this branch during an antegrade arterial stick, a precise 15 millimeter curve is mathematically required. When navigating extreme friction or severely tight stenotic lesions, operators rely on a highly specialized chemical solution, the hydrophilic guidewire. The hydrophilic polymer coating exists in dual physical states. When dry, it is highly adhesive and sticky. When activated by moisture, it becomes exponentially lubricious. This chemical property mandates a strict operational protocol. The wire must be continuously wiped with a wet sponge throughout the procedure to maintain its frictionless state. Letting it dry out strips away its mechanical advantage. Because they slide through nearly any resistance, these wires are reserved for extreme clinical applications, like squeezing through highly stenosed vessels or gaining entry into complex abscess cavities. Beyond chemical coatings, we must also account for the structural mechanics of the floppy tip design found on many navigational wires.
There is a dangerous professional misconception that choosing the length of a floppy tip is merely an arbitrary operator preference. It is actually a calculation of force distribution. This engineering force diagram compares a 1 centimeter floppy tip and a 6 centimeter floppy tip. When the wire meets resistance, it exerts focal pressure on the tunica intima, the innermost layer of the artery. A shorter floppy section drastically decreases the surface area absorbing the impact. This concentrates the force vectors, resulting in a much higher localized focal force applied directly to the vessel wall. This localized pressure mathematically correlates to a significantly higher probability of catastrophic iatrogenic dissection, meaning the physician accidentally tears the blood vessel. Therefore, the clinical mandate is absolute. Operators must always default to a longer floppy tip, like 6 centimeters, to safely distribute mechanical force. The riskier 1 centimeter tip is reserved exclusively for squeezing into exceptionally confined lesions, where a longer tip simply will not fit. This horizontal scale maps out the Guidewire stiffness spectrum. It is a continuum of mechanical capability designed to solve specific procedural constraints. On the far left of the spectrum, we find the most pliable options, categorized as noodle-like. The classic example here is the Bentson wire. The Bentson wire's primary clinical utility is testing the physical lysability or chemical dissolvability and the softness of an acute thrombus. Moving towards the center of the spectrum, we encounter standard and supportive wires. These are engineered with enough rigidity to allow for routine catheter tracking. Within this middle section, the hydrophilic variants prioritize sliding through tight anatomical spaces, whereas the standard wires prioritize providing pure structural support for the catheter. Finally, on the extreme right of the spectrum, we reach the extra stiff category. A prominent example is the Lunderquist wire, widely referred to as the coat hanger. The Lunderquist has a singular, highly specific indication. It is utilized almost exclusively to provide absolute structural rigidity for aortic stent grafting. Operating on the right side of the spectrum requires adhering to a cardinal physical law. More stiffness equals a higher rate of tissue dissection. Because of this risk, there is a strict mechanical contraindication. Extra stiff wires must never be steered or advanced nakedly through even mild anatomical curves. Forcing rigid metal through a curve prevents it from flexing, transferring all forward kinetic energy directly into a focal point on the vessel wall. To prevent vessel rupture, operators follow a mandatory protocol. Stiff guide wires can only be introduced safely by passing them through a catheter that was already pre-positioned over a conventional, softer wire. A successful endovascular intervention is never achieved with a single action. It is a modular, sequential engineering process. The procedure begins with the navigational phase. An operator deploys a steerable, hydrophilic, or long floppy-tipped wire to map out and traverse the tortuous anatomical route. This initial phase successfully establishes the foundational navigational rail, doing so with enough flexibility to avoid tearing the intima. Next comes the transition phase. The operator secures the newly mapped pathway by advancing a catheter directly over the soft wire. Finally, we enter the therapeutic phase. The soft navigational wire is removed, and a non-steerable, high-stiffness wire is introduced safely through the secured catheter. Now fully protected by the catheter housing, this high-stiffness wire acts as the ultimate rigid rail, providing the exact structural integrity necessary to safely deliver the final therapeutic payload, such as a stent. Achieving the right tool for the right job relies on understanding these distinct mechanical properties. It requires the rigorous, step-by-step application of dimensional geometry, material science, and vascular physics.